Good morning, everyone. So my name is David, and I'm excited to introduce this new tool for hydrate phase boundary predictions that we developed at UWA. So just very briefly about myself. So I did my undergraduate and master's in chemical engineering at UWA, and right now I'm towards the tail end of my second year of my PhD, where I'm looking at advanced modeling for fluid phase predictions in complex hydrocarbon systems containing hydrates. So a lot of my research interests are mainly thermodynamics focused, with a focus on modeling hydrate phase boundary predictions in particular. So the main outcomes from this presentation is that we've developed new in-house hydrate equilibrium model. So this is based on the classical van der Waals classicity model using the CK equation state as a fluid model. And we use an experimental database that we have in-house to analyze the performance of this model, and we found that on average it achieves a deviation of less than 1.5 Kelvin without any significant tuning of the model at this stage. And this statistic is applicable to multi-component hydrates with inhibitor present as well. Finally, towards the end of the presentation, I'll talk about the way forward with this tool, which is how we can further combine this model with our existing hydrate phase equilibrium database, and particularly looking at how we can enable automatic tuning of model parameters to your specific systems of interest. At the beginning of this project, one of the main motivations is that there was not really much of a centralized hydrate phase equilibrium experimental database. And so we need a large central repository, because large data sets are important for analyzing the quality of experimental data as well as hydrate models. And without an up-to-date collection of experimental data, we don't have this ability to assess hydrate models or experimental data. So we've developed a central hydrate phase equilibrium database, which can be used to perform uncertainty analysis as well as validate and tune hydrate models, and it also serves as a platform from which we can continually update with new experimental data. So I think in the previous TypeX symposiums I presented that back in August 2020, I talked more about this hydrate equilibrium database in context of safety margins and uncertainty analysis, looking at MultiFlash models in particular, so comparing the MultiFlash models. But now, since we have our own in-house hydrate model, we can use this experimental database to validate the performance of this model and look at where we can continue to make improvements. So in context of hydrate equilibrium measurement capabilities at UWA, we do have a wide range of experimental apparatus that are capable of doing this. So ranging from our hydrate nucleation cells, it's HPS Ultra, to the high pressure differential scanning kilometer. And the measurements from these apparatus will be used to inform the improvement of our hydrate phase boundary prediction tool that is currently housed in ThermoFAST. So this is I guess an overall picture of how we can leverage the experimental database. So this is sort of like the end game thing. So ideally we have the experimental database and we hook it up with models and routines that tune both the model parameters of the fluid equation state and the hydrate model, which is then fed into our standalone hydrate model that we have currently active. So because these parameter routines aren't fully developed yet, we're just directly feeding experimental data into our hydrate model for validation using preset parameters. And so I'll be talking more towards the end of that, how we can make this completely leveraged database for automatic tuning and why this would be desirable. So this is a high-level breakdown of the type of data that's available in the database. So breaking it down into terms of how many gaseous components you have in the hydrates that we actually form, and as well as whether this data is going to be inhibited or uninhibited systems. And in context of improving hydrate models, uninhibited data is the more important data because we use this to tune and validate the hydrate model parameters, while the inhibited data is used primarily to look at ways we can improve the water inhibitor interaction in the associated equation state, as well as improve our uncertainty analysis and safety margins. So this is a demonstration of ThermoFAST 2, which is an unreleased update of ThermoFAST, and I'm going to show you an example of a hydrate phase equilibrium calculation here. So this is just a simple multi-component mixture. So an advantage of ThermoFAST 2 that it's powered by standalone Fortran DLL, which means that in the future we can access what the calculation is doing in this graphical user interface in Excel or MATLAB or any other software program. So here, this is a calculation at fixed pressure. Now we can also do a calculation at fixed temperature. So before I go on to demonstrate some more preliminary results, I first want to talk about the physical foundation of the Hydrate model. So when we look at tuning model parameters, what are we actually changing in terms of the physical description? And so this is going to be presented primarily from a thermodynamics standpoint. So in order to have the potential to form hydrate, we need the presence of water and gas at high pressures and low temperatures. And so how we describe this thermodynamically is we look at the chemical potential difference of water between the hydrate phase and the corresponding iso-liquid phase that is present. And so when hydrate first is formed, you get the formation of those empty hydrate layers, and you have an associated energy change with that. So we look at the difference of the molar volume and the entropy between the supposed empty hydrate layers and the iso-liquid phase. The second part of hydrate formation is related to where does the gas molecule go, and this is the gas molecule is trapped within the various cages of the hydrate lattice. And so this process of trapping the gas molecule within the cage also has an associated energy change. And so when we come to tuning hydrate models, we either look at improving the description of the empty hydrate lattice itself, or improving the description of how these gas molecules interact with the hydrate cages and how they occupy them. And so what's important in particular is this term here, theta, which represents the fractional occupancy of the hydrate cages, so the proportion of cages that are actually occupied by gas molecules. And thermodynamically, the more the higher this fraction is, the higher the fraction is close to 1, the lower this value is going to, the more this is going to reduce the chemical potential of the hydrate phase and make the hydrate phase more stable. And so these fractional occupancy predictions are informed by something called Langmuir constants, which essentially describe the adsorption of the gas into the cage and inform the fractional occupancies. And Langmuir constants essentially look at the intermolecular forces between the gas molecule and the cage. On the flip side, accurate predictions of water fugacity and the fugacity from the fluid phase is crucial. So how we typically, this is a very simplified workflow. So you have temperature and pressure and composition input for the CPA phase state, which is used the fluid phase. And we solve for an initial TIA phase and VOE flash. And the outputs from this flash are then fed into the hydrate model. And so from these inputs into the hydrate model, we calculate associated hydrate phase water fugacity. And the hydrate phase is deemed stable when the fugacity of water in the hydrate phase is less than the fugacity of water in the corresponding fluid or ice phase. So what I want to point out is, first of all, we use the CPA phase state as the fluid phase because it accounts robustly for the water inhibitor interaction and the effect on water activity, because the CPA phase state has an additional term that accounts for hydrogen bonding between molecules that are capable of hydrogen bonding. So this gives it a significant advantage over your typical cubic, such as the Payne-Robertson or the SRK. In terms of the hydrate model, we use fixed Langmuir constants from the hydrate model source from Conte-Georges, who was the original developer and author of the CPA phase state. So these constants and parameters are tuned specifically for use of the CPA phase state. But this model does have a limited temperature range of application as we tested, so roughly between 240 Kelvin and 310 Kelvin. And then another limitation of the model today is that we haven't yet tuned the gas-water binary interaction parameters as well as they can be. So there's an improvement to be made in that regard. So now that I've established the foundation and the limitations with the model, let's look at some of the preliminary results for the hydrate model performance. When we first look at methane systems, we can see that they perform well overall. So this is some example results on the left here. And what I want to highlight is that the accuracy of the model is influenced by the temperature and pressure range that you choose, as well as the water content. So you can see here between 240 and 310 Kelvin, as shown on the left here, you get very good prediction accuracy. But if you then look to include data outside of this temperature range or data that has very low water content, the deviations begin to skyrocket significantly. So when we restrict the data to this range, is about 0.3 Kelvin average deviation. But then if you include the whole scope data, you can see it's about 2.2 Kelvin, and then looking below 240 and above 310, the deviation then begins to skyrocket as well. So this is just showcasing some of the limitations of the model at this stage. But irrespective of this, we look at extending this scope to all the simple hydrate formers. We can see that ThermoFAST 2 captures all development hydrate formers quite well. And so this is primarily using the function of predicting the equilibrium temperature at the fixed experimental pressure. And we can see that on average, the average deviation for all these hydrate formers is less than 1 in general. And we're looking at testing a significant amount of data points for each of these hydrate formers as well. So now we're going to look at some examples for binary gas mixtures. And the predictions of binary gas mixtures are quite important because getting these predictions accurate will mean you would likely get your multi-component hydrate systems to be accurately predicted as well. So here we can see that compared to MultiFlash 7, using the CPK equation of state of hydrate in MultiFlash, you see that ThermoFAST 2, while not quite as good as MultiFlash yet, it's definitely on par. And this is quite a good result, specifically because we haven't done any optimizations of the binary interaction parameters or further tuning of the Langley constants, as I mentioned. And the structure is also predicted accurately in more than 90% of these cases as well. So these are some complex mixes or multi-component mixes. And here we can again see that there's good performance comparable with MultiFlash 7. And even in this case on the right, where you see that the experimental data from this paper is not supremely high quality, you see that the pressure temperature curvature doesn't really trend well with what you would expect for a hydrate equilibrium curve. You can see that because ThermoFAST 2 performs relatively the same as MultiFlash CPK in this context, that it's performing well to display without much tuning, and we have a good frame of reference of what's going on here. So now we're looking at a binary gas mixture. So this is methane propane with a significant amount of MEG present. So we're looking at 40, 50, and 68% MEG systems. And here we're looking to see that we see that performance is on par again with MultiFlash 7. But we can see that at these high rates that MEG, the deviation does begin to increase compared to when we have no MEG present, as you can see in this table here. And what I want to highlight is that at these higher MEG dosages, particularly above 58%, that there's not really much experimental data. So here you're looking at maybe one of the three data points at 68%, and there may be 3 or 4 others above 58% MEG available in literature for all types of hydrocarbon systems. So there's really a big knowledge gap in this area. And this is something that I'm going to highlight in the next few slides, where we're looking at case study application of this hydrate phase boundary tool to field flow lines. So how would you apply this phase boundary tool in context of industry? So I guess a typical workflow is when you're looking at a development concept is you plot the expected pressure temperature profile, the pipeline from wellhead to topside, and by plotting the expected hydrate formation curve for your expected fluid composition, you can look at which regions of the pipeline are expected to be at risk of hydrate formation. What's important to realize is that this hydrate formation curve, whether generated from MultiFlash or ThermoFAST 2, is going to have some associated uncertainties and errors with it. So the two that I want to highlight in particular is that you have an average absolute deviation, which represents the overall magnitude of the inaccuracy of the model. And secondly, you also have a bias, and the bias highlights the conservativeness of the hydrate model prediction. So whether it tends to over-predict the hydrate equilibrium temperature or under-predict the hydrate equilibrium temperature. And what's important to note about these two quantities is that they will change with the fluid composition. So typically, we inject thermodynamic hydrate inhibitors, such as MEG, such that the hydrate formation curve is outside of the pipeline's expected pressure temperature profile. But if we add sufficient amount of MEG to achieve this, we can see that the uncertainty bounds for this new hydrate formation curve or phase equilibrium curve will change as a result of the MEG being added to the system. And what's critical is that when we get to longer subsea tiebacks, at greater depths where you need to add more meg to the system, there's not much experimental data available. So because of the lack of data, we can't be confident in the values that we generate or the uncertainty in the bias. And so that's something that we need to have more data to be able to improve our industry safety margins. So let's look at this in the context of some actual multi-component experimental data with meg present. So this is the fluid composition that we're looking at here. And here you can see that 10% meg measurements are accurate in this case, but obviously not enough to have complete hydrate formation in the pipeline, completely prevent hydrate formation in the pipeline. And again, 28% meg is quite accurate between what ThermoFAST and MultiFlash calculates. And in this case, 38% meg is effectively enough, as predicted by ThermoFAST and MultiFlash, to ensure prevention of hydrate formation, which may be very slight under inhibition. And so you can see here that both ThermoFAST and MultiFlash capture the experimental data well at these low meg concentrations. So these are the average deviations in this table here. And you can see that for both ThermoFAST and MultiFlash, that they're less than what's typically used as an industry safety margin of 2 Kelvin. However, because of the other associated uncertainties, such as what's the actual composition of the fluid in the pipeline, how much meg is actually there in your given local area, or the expected pressure temperature profile, what deviations are going to be associated, there's not actually too much reinforced savings of meg dosage in this case. But if we now look at systems that have above 48% meg, we begin to see much bigger deviations in the models compared to the experimental data. So here we can see that at 48% meg, we already have a deviation maybe of 2 Kelvin on the order of 2 Kelvin. And with 58% meg, you can see that these deviations are also present. And in this case, ThermoFAST 2 predicts that 58% meg would be just sufficient enough for total inhibition of the pipeline. But in reality, you can see that the experimental data is maybe 2 to 3 Kelvin to the left here. So these are the average absolute deviations as calculated by ThermoFAST and MultiFlash. And the main takeaway from these slides, I guess, is highlighting the bias and why the bias is important. So here we can see that both ThermoFAST and MultiFlash are tending to overpredict the hydrate equilibrium temperature compared to experimental data, which means you're dosing more meg than you actually require to achieve hydrate inhibition. If we then apply your typical 2 Kelvin safety margin to the system, so let's say we look at this specific point here. So ThermoFAST 2 is about 271 Kelvin. If you then add another 2 Kelvin, then your hydrate curve goes to the right here, and then you actually need maybe 2 or 3% more meg based on that extra safety margin that you apply. But because the bias of this model is conservative in this case, that means you're adding meg dosage to inhibit the hydrate formation curve 4 to 5 Kelvin more than we actually need, because the experimental data is actually further to the left. So this is how we can use both the uncertainty and the bias to play around and optimize our safety margins, even if the model is not as accurate as it could be. But what's important is that we need to have confidence in the uncertainty margins and the bias of the model by having the experimental data to back this up. And so we need more high rate % meg data specifically to be able to validate and use these bias and the uncertainty of the model. And also another thing to note is that this is for a fluid that doesn't have any carbon dioxide present. So if you have a field such as Gorgon that has a high amount of carbon dioxide, the results that you see here won't necessarily apply. You might not have a conservative model in that case. You might actually have a model that tends to underpredict the hydrate equilibrium temperature. And when that's the case, you need to be careful, because those are the cases where the safety margin is critical to prevent hydrate formation in particular, because now you need that safety margin to ensure that hydrate isn't forming. So now I want to look at the way forward, which is discussing this concept of an automatically re-tuneable model. So why is this desirable? So firstly, it enables flexibility and it improves prediction accuracy. So the main idea is that rather than tuning your parameters to all of the experimental data available, you tune your parameters to specific subsets, and namely you tune them to comparable systems only. So let's say you're looking at a multi-component system with high amount of carbon dioxide, and you have an expected pressure temperature range, then you tune only to experimental data relevant to that composition and that pressure temperature range. Secondly, it ensures the model's performance is up to date with trending experimental data. So as we continue to get new hydrate phase equilibrium experimental data published, as well as measurements that we take in-house, it ensures that this actively updated database will have the best parameters available for the model for the given data. And it also allows for user input experimental data method, as I mentioned, so looking at in-house measurements. And if you have field fluids that you would like to have measured, and we have the equipment available to be able to take measurements and improve our model based on the fluids that you have available as well. So in terms of the methods to verify model and tuning performance, so this is sort of a model that's borrowed from machine learning concepts. But the idea is that when you have experimental data, it's important to be able to verify the model performance against test data that the model has never seen, and then use a set of training data to tune the model parameters against. So the idea is that you split your, in this case, methane hydrate data into these two subsets of training and test data. So you can train the model against some methane hydrate data, and then when you have some test data as well as cage occupancy data, which we can independently validate the model against. So we're using hydrate equilibrium temperatures, and by evaluating the predictions against the test data, then we can see if the model is a good fit for that specific parameter set. And what's really cool about this method is that we can be sort of flexible and creative with how we develop our automatic tuning parameter algorithm. So the experimental data splits can be handled as splitting specific data sets, or we can split them at random proportions. But by having this large experimental database available, we can also identify which data sets are going to perform well and which data sets are high quality. And we can also choose to specifically eliminate specific data sets that aren't consistent with other hydrate phase equilibrium measurements. So we have a lot of freedom to develop the automatic parameter tuning algorithm that will give the best results in 90% or more of cases. So to round it up, so I've showed you the newest improvements and update on our in-house hydrate phase equilibrium model using the CPA equation state. And we've shown that it achieves that 1.5 Kelvin deviation or less on average without tuning. And I've talked about how we can combine this model with our database to develop improved automatic tuning algorithms is of interest. So to conclude, I'd like to thank my supervisory team, Zach, Eric, and Bruce, for giving me a lot of support and guidance on my way so far, as well as Dr. Peter Falloon, who did a bulk of the work developing the current ThermoFAST to graphic user interface, as well as KBC for providing the MultiFlash license to help further validate our hydrate equilibrium tool. Thank you.